If you're anything like me, then you probably are fascinated by black holes. You know, those mysterious objects predicted by Einstein that are effectively eternal prisons for anything that is unfortunate enough to cross its event horizon. Well, if you've been following recent news, then you may have heard that we've seen the back of a black hole, but what does that even really mean? So today what I want to do is to try and explain what these Stanford astrophysicists have found in this recent Nature paper that's called Light Bending and X-ray Echoes from Behind a Supermassive Black Hole. First off, let's just try and set the stage with some context. So first off, we think that every massive galaxy contains a supermassive black hole at its center, and some are considered quiescent, which means they're kind of quiet, there's not much going on around the center, and then there are some that are considered active, which means they have a lot of activity, like this one galaxy that the Stanford astrophysicists were studying. It's called 1 Zwicky 1. An active black hole means that there's just like a high level of luminosity or brightness at their very centers that's just due to the black hole sort of feeding on material at the center. So typically, supermassive black holes that are active will form what is known as an accretion disk, which is just sort of this spinning disk of material that's flattened, that's orbiting the black hole, and this disk is typically made up of like gas and stellar debris and dust and stuff like that. But because the black hole's gravity is so strong, the material in the accretion disk actually gets sped up faster and faster, and when things get energetic enough, they tend to radiate energy. And in this case, the astrophysicists were looking at the X-ray regime of the electromagnetic spectrum, which is a very high energy part of the spectrum. And specifically, they were looking at this transition known as the iron K alpha transition, which is this particular transition in the iron element that happens in the X-ray regime. What the Stanford astrophysicists are claiming is that there are X-rays being emitted in the corona. So effectively, if you have the accretion disk, you have the corona up here. And the idea is that those X-rays are hitting the accretion disk and are being reflected effectively into our line of sight. And these X-rays are being emitted and hitting the accretion disk on the near side to us, so that's sort of the side that's facing me, and then on the far side, which is behind the black hole, sort of representing the side that we shouldn't normally be able to see and closer to the camera. But the idea is that the observations can be explained by light hitting the backside or the far side, and because of the strong gravity of the black hole, the light essentially gets bent towards us. And I just hit the microphone, so sorry if you heard that. But essentially, the light hits the backside, and because of the strong gravity, the path that light has to take gets bent into our line of sight. So that's effectively what they're claiming. But there's just a ton of complicated physics that goes on in this process, and I'm going to try and explain all the different things that the astrophysicists consider. From what I understood, there's a number of different effects going on. So this is not a really good representation of the accretion disk because effectively this is all rotating together effectively. And the idea is that in accretion disks you have more of sort of like a differential kind of rotation. That is, the rotation speed at different radii is different. And so because of that sort of relative motion, as in part of the accretion disk is moving faster than other parts of the accretion disk, you have a Doppler shift of the light. So essentially the observed wavelength or frequency of light that we see on Earth is shifted relative to when it left the accretion disk. And then also because the gravity around this black hole is incredibly strong, you have effectively gravitational redshift. So what gravitational redshift is that the light effectively will lose energy as it escapes the area that's near the event horizon. It can't escape from the event horizon or past the point, but if it forms very close to the event horizon and tries to escape from it, the gravity there is so strong that effectively the light loses energy, which is related to its wavelength, which means we'll see a different kind of color of light when it gets to Earth effectively. And the astrophysicists have created models that attempt to simulate all the observed, X-ray emission light, and they've effectively modeled what is known as the light curve. So what the light curve is essentially this plot of like the energy or the amount of counts of X-ray photons you get as a function of time. And these models try to account for all the different kinds of physics going on. So essentially all the general relativity, all the radiative transfer, which is essentially the physics of how light and matter interact with each other. And they've concluded that the flaring of X-ray emission, that is sort of these spikes in brightness over time, is consistent with photons coming from behind the black hole. Now, again, like I said, I'm no expert in this area, but I had a few questions when I read this. My first question was, are there any other models that could possibly explain the phenomena that, that doesn't involve light coming from, the near side, or sorry, the far side of the black hole? And the answer was yes. So they did test a number of different possibilities. So one thing they tested was known as they changed the variability in the X-ray emission. That is, sort of changed the amount of time the X-ray flaring happens. And can that explain what they saw? And the answer was no. They also explored the possibility of like radial outflows coming from sort of the accretion disk area. So just sort of material just being sort of just shot out. And could that explain the flaring that was seen? And apparently no. And then apparently they looked at how the accretion disk is ionized by the coronal X-ray emission. So just how does the light from the corona, how does that affect the interactions with the atoms in the accretion disk, and could that affect what they saw? And the answer was no. So apparently they've tested, to the best of their knowledge, all the possible other scenarios that could explain this, and they aren't consistent with the data. And my second question, because some of you may know, I'm a supermassive black hole weigher. I dynamically weigh supermassive black holes, but typically those in quiet, quiescent, non-active galaxies. So this is not in my area of expertise. But I wanted to just know, how did they account for the black hole mass, and how does the black hole mass actually affect the expectation of this discovery? And what I found out was that in these models, they had the black hole mass as a free parameter. That is, it's a number that they effectively try to find through the model optimization. So you have a model, you have a number of parameters in it, and you essentially change the parameter values over different iterations. And because you're changing the numbers, you're going to get some good representations of the data, you're going to get some bad representations of the data. And the idea is to find the best set of parameters that recreate the observed data. And so what they found was that the best black hole mass was about, I think, 31 million times the mass of the sun. And this is in an active galaxy, so I wanted to know if it had a previous measurement with reverberation mapping, which is the standard technique you use to measure the masses of black holes in active galaxies. And indeed, they had two prior reverberation mapping measurements of the supermassive black hole. One was, I think, 28 million, which was consistent with what the Stanford astrophysicists found. But there was one that was also only like 9 million, which I think the Stanford astrophysicists have claimed that it's just, it wasn't a robust measurement because of some certain factors. So effectively, they're getting consistent results with the prior reliable measurement. And, with that, that's all I really have to say about this discovery. It was very exciting to learn about. But before I go, I do want to point out that while this was the first time we've seen light from, behind a black hole, this is not the first time we've seen light bent behind or, gravitationally lensed by a massive object. In fact, the reason why Einstein became so famous was due to the fact that Arthur Eddington observed this phenomena with starlight from behind the sun. So effectively, the sun, there was a total eclipse in 1919, and Eddington went on this expedition, and he was able to observe the bending of starlight from a distant star from behind the sun, which you would not have been able to see if you assumed, the standard Newtonian gravity model. It was essentially this confirmation of Einstein's theory that made Einstein so famous overnight. We've known this phenomena for, over 100 years now, this sort of idea of light being bent around a massive object. But, I just think it's super cool with this, 1 Zwicky 1 discovery that Einstein was just a total genius. It just further confirms his theory, and how 100 years of technological advancements and development have enabled us to observe these just really cool confirmations of Einstein's theory in outer space. So it's absolutely incredible. And with that, I just want to say thank you for watching. If you like what you saw, please consider subscribing and turning on that notification bell for more videos from me, and I will see you next time.